So as you can see, sometimes it's helpful to find just the dy, to realize that in the derivative, dy dx actually represents the change in y over the change in x, and sometimes we just want to find out what the change in y is. So here's some problems here that we're asked to find just dy. So the first step is actually to find dy dx, which is basically the same thing we've been doing by finding the derivative of this equation. This particular problem requires us to use the chain rule. So the derivative of the outside, 8 times whatever the inside function is to the 7th. I remember the chain rule says to leave the in alone, and then to multiply it by the derivative of the inside. Okay? But remember the direction said to find dy. So if we want to find out what dy is, and we know what dy dx, it's real simple. You multiply both sides by dx. And so dy turns out to be this equation times dx. Okay, so it's kind of just one extra step that helps us find out, again, the linear approximation or the difference in y. Okay, so let's try some other examples here. So once again, I'm going to find dy dx, and this one's going to require me to use the product rule, x squared times tangent of x. So derivative of the first times the second, plus now I'm going to leave the first alone, and the derivative of tangent, remember, is secant squared x. Once again, I want to find dy, so I'm going to multiply both sides by dx to get this to cancel. And when I multiply that by dx, I then get dy equals that equation times dx. Notice here that because of the times, we want to multiply the whole thing times dx, so it is important that we put parentheses here. Because of the addition problem, we actually want to add first and then multiply that answer by the differential dx. So just a helpful hint on notation. Okay, so let's take a look at the next one. This is a little more complicated one. This involves trig. So again, I'm going to find dy dx. And before I get started here, I realize, oh, this is the same as the cotangent of x, the whole thing squared. That helped me derive this because I'm going to have to use the chain rule here. So I'm going to derive the outside, 2 times cotangent of x to the first power, times the derivative of the inside. Remember the derivative of cotangent is negative cosecant squared x. Okay, so remember I want to find out what dy is, so I do the last step by multiplying both sides by dx. And so dy equals this. I don't need parentheses here because there's no addition or subtraction sign. Remember that's a negative sign, not a subtraction sign. That time sign helps me with that. So there's my answer. Okay. Next problem here is 6 to the square root of x, and I don't know how to derive square root functions. So the key to this one is to change this to something that I can use the power rule on by changing the square root to the 1/2 power. They're equivalent, but now it's easier to find the derivative. So once again, dy dx equals, this is a straightforward power rule, 3x to the negative 1/2, and again I'm going to multiply both sides by dx. And so dy equals 3x to the negative 1/2 times dx. And just for future reference, 3x to the negative 1/2 is equivalent to 3 over the square root of x. So especially if this was a multiple choice question, this might be what it would look like in your choices. So you need to be aware that x to the negative 1/2 and over the square root of x mean the same thing. Okay, and so here's some problems where we ask us to find the equation for the indefinite interval. In other words, we want to find the equation y equals something. But notice they give us dy equals something times dx. So this is sort of backwards what we had to do first. The first thing we want to do is get rid of the dx by dividing both sides by dx. So we end up with dy dx equals this equation. And then to get rid of this is an antiderivative idea. I then have to antiderive this equation. And this is the anti-chain rule. Remember, that's the antiderivative of the outside. So in this case, the outside function is to the third power. So it's 1/4. And I'm going to raise the exponent by 1 with respect to the in. So I'm going to leave that alone. But then remember, I'm going to come back here and divide by the derivative of the in. So in this case, I'm going to divide by 3. So I'm going to write times 1/3. And then always go to the ocean plus c. So really important that you understand where the 1/3 comes from. It's dividing by the derivative of the inside function. Okay? So let's try a couple more examples. Again, I'm going to divide by dx first, and then antiderive this equation. to get y equals, okay, so antiderivative of cosine of 2x. My outside function is cosine. So I'm going to antiderive the outside with respect to the in. Remember, I'm going to divide by the derivative of the inside. So in this case, 2x, I'm going to divide by its derivative, which will be 2. So I'm going to go times 1/2, and again, go to the ocean plus c. Okay, so let's try the next one here. So again, I'm going to divide both sides by dx, and then antiderive what's left. Well, this one is just a series of power rules, or anti-power rules, sorry. You're going to antiderive each one separately. So the first one, if I add 1 to the exponent, you'll get x to the 5th, and divide by that new exponent, it'll be 3/5 x to the 5th. Minus, if I add 1 to the exponent, it'll be x squared, and 2 divided by 2 actually comes out 1, so I just get 1x squared. I'm not going to write the 1. Plus 8x, that's like 8x to the 0, so when I add 1, it becomes 8x to the 1st, plus my constant, and so there's my antiderivative, which would be equal to y here. Okay, so when you're dealing with differentials, it's really not any different. Just one extra step, either multiplying both sides by dx, or if you're antideriving, you divide both sides by dx. So relatively simple, not much different than what we've been doing.